All right, guys, so we're going to start topic 7 and hopefully finish this in one video because it's a pretty short lecture. Okay, so we're going to start with combined loading. And the nice thing about this topic is that it doesn't require any more theory than what we've already discussed in the past two topics. So all we're doing right now is we are going to apply all of our different stress formulas, our internal stress formulas, to figure out what happens when we have a member that's subjected to multiple types of stress at the same time. And all we have to do is analyze the system in the same way that we've been doing it in all the other topics, but we just use the method of superposition to kind of add everything together. So we'll go through some of those examples in this topic slide, and then we're also going to analyze one new type of system, which are called thin-walled pressure vessels. And they have some very specific applications in civil engineering design, so they are important to know. And those will be a little bit different than what we've talked about, but still a pretty quick to grasp concept. So we're going to actually start with thin-walled pressure vessels. And what these are, I have a picture of them later, but what they are, they're cylindrical or spherical. So they come in those two categories, and we'll see the difference between those later and which ones are kind of more efficient for design and what the advantages of each are. But they're often used as boilers or tanks, so to hold some kind of liquid or gas, and which that means that there's some kind of internal pressure that's acting on the system that we have to account for when we design. So when these systems are under pressure, what happens is the material is subject to loading from all these different kinds of directions. And we have this very simple way to analyze these systems when the walls are thin. And most of the time when we're designing these systems, especially to hold things like water or certain types of gases, we purposely design them to be thin-walled. And that's why there's this whole category just on thin-walled pressure vessels as opposed to thick-walled pressure vessels. So a thin wall, what does that mean? It's not kind of just up to you to decide if something is thin or thick. It's not subjective. There's actually this very easy ratio that we use. It's if the radius is less than your thickness value or equal to 10, we categorize this as a thin wall, okay? So we can assume if this is a thin-walled pressure vessel, we can assume that the stress distribution is constant throughout that thickness. And what happens is, if we actually set this ratio equal to 10, you'll get about a 4% error in your calculation. So you'll see that the larger this ratio is, the smaller this ratio is, the more that error increases. And the larger the ratio is, which means that your radius is super large compared to your thickness, the smaller that error is. So we like to see large values for that ratio. Okay. Oh, and one last thing, when we talk about pressure in the vessel, this is just the gauge pressure, which is basically a measure of the pressure that we are exceeding atmospheric pressure. Okay. So we're going to start by talking about cylindrical vessels, and then we'll go on to spherical, and then we'll just go right into an example without having to derive too much this time. So cylindrical vessels, we have the wall thickness T, the inner radius R, which means the radius to the inner portion of that system, not the outer portion, but really it wouldn't matter because they're technically very thin, but it still is the inner radius. P represents that gauge pressure. And then we have two different types of sigmas or normal stresses here. We have the circumferential or hoop direction, and then we have the longitudinal or axial direction. And you can see in this figure here, these two figures, what the difference is. So this sigma 1, it's kind of hard to see what's happening, but basically if you were to make a cut around the hoop, like your cut is actually this if you're cutting the hoop in half, as opposed to here where you're cutting this at the cross section of that vessel. So in the radial, this is like a radius that's being exposed for sigma 2. Okay, and we have these two functions here for normal stress that are functions of this P, R, and T. So all we have to do is really plug into these two equations, so as long as these are thin-walled. Okay, spherical vessels, we don't really have to worry about different sigmas because since this is a sphere, no matter how we cut it, we're going to get the same sigmas. And when we do isolate that little differential block, we see that sigma 2 and sigma 1, or any sigma at the face of this block, is equal. So really all we have to worry about for spherical vessels is plugging into sigma 2. And the reason we have this as sigma 2 and not sigma 1 is because it's actually equal to the sigma 2, that longitudinal or axial direction that we calculated for cylindrical vessels. So it's just really these two equations, and they apply to everything here. So that's all we really need to know to kind of jump right into an example. So we have a cylindrical pressure vessel with an inner diameter of 4 feet and a thickness of a 1/2 inch. And we want the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component exceeds 20 KSI. And then we also know that under these same conditions, what is the maximum internal pressure that a similar sized spherical vessel can sustain? So we're going to kind of compare these two types of vessels and see which one is more efficient. But first, let's start with a cylindrical. So these two pictures here, this actually is a cylindrical vessel, the first picture. And this is a spherical vessel. You can see the difference here between them. And you can also see that that cylindrical vessel has some inner radius. It's a hollow tank. And if we cut it at the cross section or we cut it across the hoop, we're going to get different values of stress. But no matter where we cut that sphere, we're going to get the same kind of values. So let's come here. Let's start with the cylindrical. I did not spell that right. Let me try again. Okay. There we go. Okay, so the max stress is going to be in our circumferential direction. You can plug in both of these, but you can already kind of see, just given what they're telling us, this is going to give us that max value of stress. So let's plug in our 20 KSI. We're solving for this max internal pressure, so P, times our R value, which is 24 inches. And then, so the way I got this, the diameter is 4 feet times 12 inches per foot. That's going to be 48 feet divided by 2 is equal to 24 inches for the radius, because this was the diameter. Okay, so that's where I got the 24 from. And then the thickness is just a 1/2 inch. So here I can solve for P and I get 417 PSI. And really that's all the problem was asking for, just that P value. Okay. Now what we have to do is we want to figure out for the spherical, gosh, I can't spell today. For the spherical system, we only have this sigma 2 to plug into. Okay. And we can directly again plug in this 20 KSI. And then now we have the 2 times 1/2 inch. And here we get the P value of 833 PSI. So we have a larger max stress that can be carried here. And one thing to note, although we have, so here we technically do have a sigma 2 value here that's also equal to 833 PSI. But in this case for the cylinder, this doesn't apply because this is smaller. So we don't want to push the system to 833 because it won't be able to hold it in this circumferential direction. So that's why we only go with this 417 for the cylinder. If we're talking about the sphere though, we only have to abide by this formula, which means in any direction I can push the system to be 833 PSI. So what we see here is that in all these cases, the spherical system is basically double the strength. It can carry double the amount of pressure inside than the cylinder. So you may be wondering, why don't we always just design these in the cylinder, in a cylindrical sense, and why do we even, in a spherical sense, if they're so much more efficient? Well, it's because these types of systems, these spherical systems, are very hard to fabricate. So you have to kind of leverage whether it's worth it to spend the extra money or a fabrication design on building the spherical system, or if you don't need as much pressure, to just go with a cylinder. Okay. All right. So let's move on. State of stress. Now we're going to get into combined loading. So that was really the most new part of this topic. Everything else is going to be stuff that we've already talked about in previous topics and just kind of combining them for a kind of comprehensive review. So we have already talked about how to develop basically distributions for internal axial force, shear force, bending moment, and torsional moment all separately. And now what we're going to do is we're going to talk about how do we analyze these systems when multiple things are happening simultaneously. And this is often what happens in the real world, right? We can't just say, oh, this is only going to have stress due to bending, or this is only going to have stress due to axial load. Sometimes we can say that one is so large that it's going to take precedence over another, but it doesn't always work out like that. We do have to be conscious that there are situations where that's not always the case. So here what we want to do is all we need to do is actually use the method of superposition and calculate the internal stress from axial force, shear force, bending moment, torsional moment, and kind of add up what we know about these, as long as these stresses continue to have a linear relationship between stress and load, and that the geometry does not significantly change after loading. And we do know that what we're talking about in this class, we're talking about all linear elastic deformation. And so really, if our system is just not too deformable, we'll be fine, which is the case for most of our structural systems. We don't really design anything that's going to be extremely deformable, like a trampoline or something that you can stretch very easily, like a rubber band. Okay, so I took these screenshots from the book because they were actually really helpful in giving kind of a nice overview of everything. So this is just a general procedure for analysis, and it talks about what you have to do in terms of internal loading, and then also each stress component that we've already talked about. So if we come to this side here, you see this is for normal force, shear force, bending moment, torsional moment. This is the thin wall pressure vessels that we just talked about. And then superposition here allows us to kind of add everything up. And let's just not forget though, one thing is we are not adding up stresses that don't act in the same direction. Superposition means that if I have an arrow in this direction of some magnitude and an arrow of some magnitude, I can add all of these up. But if I want to add different directions, I have to now use vectors. So I cannot just sum those in a linear sense. So be very conscious of that when we're doing problems. We can't just add shear and normal force in that sense, but we can keep them separate and add all the normal forces together, add all the shear forces together. Okay, so let's try this in an example. We have a force of 150 pounds applied to the edge of the member that's shown here. We're going to neglect the weight of the member and determine the state of stress at points B and C, which means basically whenever you hear state of stress, we want all of the stresses acting at B and C that we can figure out from the loading. Okay, so the first thing is, I have a picture here. This is the internal loading. You always want to start by the internal loading because that's how we get the stress. So even from our previous topics, we always want to make those cuts because we have to expose those internal forces in order to get stress. Stress is an internal reaction. So that should always be your kind of go-to. This has to be number one. So if we make a cut, I put this here because it's a lot easier to see in 3D like this than if I were to draw it. So we're sectioning this member through BC here. And in order to maintain equilibrium at this point, at this section, we have to have an axial force of 150 pounds that acts along that centroid to push back down. And we have to have a bending moment of 750 pound-inches about the centroid, or about that principal axis, right? Because this is an eccentric loading here. Okay, so here, after we've developed this internal loading, all you have to do is equilibrium to get these two internal loadings. Now we can do number two. I'm going to put it here even though it's above it, but these are the stress components now. Okay, so the first thing is we have a uniform normal stress distribution due to that normal force. So we have sigma, and we know we have 150 pounds divided by the cross-sectional area. And we get 3.75 psi. And then we can use now the stress due to bending moment. So we have normal stress distribution due to bending moment, and this is going to be sigma equals mc over I. And we have 750 pound-inches times, the C value of 5 inches. And then we have the moment of inertia of the system, 4 times 10 cubed, and we get 11.25 psi. Okay, and now if we want to, I'm going to actually come back down here. I think I have pictures somewhere here for you. I put them way down. Okay, now I have these pictures because I want to show you what we just calculated. So here we have calculated the normal force. We've calculated the stress due to bending moment. And we want to now figure out the combined loadings, but we need to be careful with our signs. That's the most important part here. So step 3 here is going to be superposition. Okay, so I'm going to start with sigma at point B. And I want to look here and say, okay, well, the 3.75 is in compression. So that's going to be a negative P over A. And then the MC over I at point B is in tension. So I'm going to say that's a positive MC over I. If I want to do the same thing for sigma at C, also negative P over A, the whole thing is pushing onto the system, so compression. But now at point C, I'm also experiencing compression. These arrows are pushing in like this, compressing, while at B they were in tension. So now I'm going to subtract. So if I put everything, kind of plug and chug what I have a negative 3.75 plus 11.25, and I get 7.5 PSI, and this is in tension. And here I get negative 3.75 minus 11.25 equals negative 15 PSI in compression. Okay, if you needed help figuring out the directions of all of these, this is where those derivations really come in handy that we had kind of gone over, and I tried to go over really slowly in the other topics to show you when you bend the system or you apply torsion or you apply whatever kind of force you're applying outside, how the internal system is reacting to that. So you just want to think about what the force or moment that's being applied to the system is doing in terms of compression and tension. And that's how you can determine these signs here and these diagrams, these stress diagrams. So if you're having trouble figuring these values, the positive and negatives out, go back to the axial force and bending moment topics and go back and look at how we derived these stress distributions. These are stress profiles. So go back to that video and make sure you get why these are positive or negative and how the neutral axis point is that point of zero stress. And we can actually calculate that. So if they didn't ask for it in the problem, but let's say we wanted to find the location of zero stress. We can actually use similar triangles because we have these stress values. So we could say 7.5, and I'm doing that for this. 7.5 is to the location X, as 15 is to 10 minus X, and we get X is equal to 3.33. This value right here. Okay. All right, so let's try another one of these. This is going to be a thin-walled pressure vessel example. This one is a little bit more involved, so let's work through this one a little slower. Okay, so let's read through this actually. We have a tank here and it has an inner radius of 24 inches and a thickness of 0.5 inches. It's filled to the top with water having a specific weight that's given, and it's made of steel having a specific weight of this. Determine the state of stress at point A, and the tank is open at the top. So you're going to kind of have to remember your equations for weight of water in terms of density, but those will be given to you. You don't have to memorize these. And this procedure is a little new, so if you're having trouble following along the first time, that's okay. It's because we haven't really done anything like this yet in this class. And I won't actually ask you to reproduce a problem like this, but it's good to know the concepts that are going on here. So I might ask you conceptually about these kinds of problems, but I won't ask you to reproduce them. Okay. So let's start again. Always number one, we want to start with the internal loadings. Okay, so I actually have a picture here so that, again, we don't have to draw this, but there's just some things to note. The weight of water here is supported by the water at the surface just below each section, not by the walls of the tank. And that's because we don't have we don't have a top. This is an open vessel. So we're going to make the assumption that the water column is supported by its own self weight, so not by the walls of the tank. And then in the vertical direction, the walls simply hold up the weight of the tank itself. Okay, so with that being said, we can get the water as gamma that's given, there's a weight of steel, gamma of steel. And here, if we plug in these values, we have, this is given 490 pounds per foot cubed. And then here we have pi times, this is going to be 24.5 over 12, because I want this in inches. This is inches, yeah. I want this in feet because my specific weight is in feet. So to get it into feet, divided by 12 squared, pi r squared, but minus the inner area, I should say, actually. Okay, and then times here 3 feet for the entire length of the column that I'm looking for. And then here I get 777.7 pounds. Okay, so this is the weight of the steel. So this is just the area of that column times the height, right? So what, let me, in case this was confusing. This is specific weight this is volume to get this into a force, right? Because I want to cancel out that feet cubed, which I just did. Okay. Now, the stress in the circumferential direction developed by the water pressure at level A. That's what we're trying to get. So we're looking here at point A. And to obtain this, we have to get that gauge pressure. So we're going to use this gauge pressure value. P is our gauge pressure of the specific weight of the water times that place where we're looking for, which is the 3 feet, times that distance. So this gives the pressure at a point located at a depth Z in the water. So let me write that here. In the water column, okay? So then we can say the pressure on the tank at level A. I'm just going to plug into this equation. We have specific weight of water, 62.4 pounds per foot cubed. And then we multiply that by 3 feet, which is the depth of point A. And we get 187.2 pounds per foot squared. And if we want to convert this into pounds per inch squared, we get PSI. Okay. So now that we have all of our internal loadings, step 2 is to get the stress components. Okay. And this is a cylindrical pressure vessel. So we know that we have these 2 components, sigma 1. We'll start with sigma 1. So the first thing we need to do always is we need to check this is thin-walled. So actually, before I even write sigma 1, let's check that this is thin-walled. So I'm going to say R over T is equal to 24 inches divided by 0.5 inches, and I get 48, which is greater than 10, so we're good to go. It's thin-walled. Now I can actually start with my sigma. So let's start with sigma 1. And I have an inner radius of 24, so my sigma 1, which is PR over the thickness, is going to be that 1.3 psi times my inner radius of 24 inches divided by the thickness, which is 0.5, and I get 62.4 psi. And then I need to figure out my sigma 2, and this is basically, remember, the weight of the tank is supported uniformly by those walls. So for sigma 2, I need to use the weight of that column divided by the area. This is just force divided by area. Divided by the area of that system. can leave it in inches, okay? And basically, we don't need to do a sigma 2, we don't need to use, so just as a note here, let me write this here, sigma 2 of this function, it doesn't apply here because the tank is open at the top, and so we're saying that the water doesn't develop a loading on the walls. This is an assumption we make. So we're saying because this is open at the top, the water is supported by the water below it, and it's not exerting pressure on the walls. And in order to apply this equation, we would have to have that longitudinal pressure in that direction, sigma 2, because we know that that's when we're making that cut, and we have to have that pressure. So because we're not making that cut, we don't have that pressure, we don't need to include this in our calculations. The weight, the normal stress due to the weight of the steel, of the cylinder itself, and the pressure due to what we had calculated previously, just the depth of water at that point, is enough. Okay. And then point A is basically subject to this biaxial stress. I think I put, oh, I didn't put a picture, but that's the solution that we're looking for, the sigma 1 and sigma 2. Okay. So we're going to do another example. This topic is basically all just a bunch of examples because we're just applying some stuff you already know. So bear with me. We have 2 more and this is all done. Okay. So here we have a little more of a familiar structural system. We have a frame, and this frame has a rectangular cross section, and we want to know what the state of stress is that the loading produces at the specific point C that's given. Okay. So the first thing I'm going to do here is I'm going to calculate the reactions from the pin and the roller. And I'm actually going to put them here for you. And I'm going to let you guys calculate these. And if you have trouble getting these values, leave a comment and we can go through those. But this is, you guys should all be pretty good at the statics part by now. So I'll tell you the procedure that you can use to get these, and then try this on your own and make sure you can get these values. So if you sum moments at point A, you'll be able to directly solve for B. And then you just sum forces in the X and Y, and you can solve for the other 2 unknowns. Okay, so this is a determinant system, no tricks needed, you're all good. Okay, and we have the resultant force here of 125 kilonewtons. So we're specifically asked for the stress at C. So let's make a cut at C. And this would be like 1 internal loading. So we're going to make that cut. Let's say this is point C. And every time we make a cut, we have to remember that we're exposing some internal forces. So V, N, M. I'm drawing N in this direction, even though it's usually drawn in the other direction, just because I already know what the value is going to be, because I have a 16.45 pushing in compression. Usually you would draw it assuming positive. I'm just going to draw it that way because I know that's what's happening. And then here at point C, it's 1.5 meters away. This is my point C. Okay. So again, I can solve for all of these using my equations of equilibrium, sum of forces in the X, Y, and sum of moments, and I get these values. N is 16.45, V is 21.93, and M is 32.89. Okay, so now that the internal loadings are done, step 2 here is to solve for the stress components. Okay, so the first one we have is normal force, right? So we have sigma C is equal to P over A. And we just plug in the normal force, because this is normal stress. Cross-sectional area. And that was given right here, if you wanted to see where the cross-sectional area was. It's given in the problem. Next, we have shear force. So what we want to see here is something interesting. C is located at the top of this section, point C. Right here you can see it's located at the very top of that section. So what happens here is our A prime, the area above, is 0 since C is located at the top of the member, which means our Q value, which looks like this, is 0, which means our shear stress is 0. So we don't have to do anything there. The last thing we have to do is bending moment. So here, our y, so actually let me write the equation first. Over I. So our y value, or you can say it's my over I is equal to c, is equal to 0.125 meters from our NA, right? So if I want to plug this in, sigma c is going to be 32.89 times 10, just that internal load that I already solved for, times 0.125 meters divided by 1 over 12 meters. And I get sigma C is 63.16 MPa. And now through superposition, these are both positive. I get sigma C. So actually, let me write this as number 3. Okay. Not too bad, right? One last problem. Okay, oh, and here is the sigma value from the normal force that we calculated, sigma from the shear force, and sigma from and tau from shear force, and sigma from bending moment. The tau is 0, no need to add anything there. And then we just have to add sigma from bending moment and from normal force. Okay. Last example, number 5. So a rectangular block, let's see if I can finish this before my iPad does. Okay. A rectangular block has negligible weight and is subjected to a vertical force. Determine the range of values for the eccentricity EY of the load along the y-axis so that it does not cause any tensile stress in the block. So what this is asking for is, where can I put P on this block so that this block doesn't experience any tension, and specify the region on the cross section where P may be applied without causing a tensile stress in the block. Let me read the difference. So we want to know the values for EY, and then we want to specify the region. So that's just going to be in like a picture. So let's start basically. When P is moved, let's say we want to move P to the centroid of this section. Okay, what happens is we need to add a couple moment to account for that if we want to move P to the centroid. So we would have to say P times EY. Okay, and this is, so if we move P to center, must apply to maintain equilibrium. Because this is a force now that has some distance, which means it's a moment, okay? So our combined normal stress at any coordinate location y on the cross section that's caused by these two loadings now. So I need to consider two loadings. I need to consider moment and axial force. So our combined loading, this sigma, we were interested in knowing negative P over A minus this M value, okay, divided by I And this is what I'm interested in knowing. So I'm going to take out this negative P over A and simplify this. Okay. And I'm interested in keeping this in compression. So basically, for any positive value of EY, so for a positive EY value, the smallest compressive stress occurs along AB. So smallest sigma in compression occurs along AB when this Y value is negative H over 2. Okay, in the negative direction. So P causes compression there, but the MX is going to cause tension. So this is what we're trying to say. This minimum value is when when Y is H over 2. So we're plugging this in here. It's H over 2. Okay. And this is in compression. So in compression, this will stay negative as long as 1 is greater than A EYH over 2IX, as long as this stays positive, because a negative times a positive is a negative. If that becomes negative, then we're going to cancel out and get tension. So here, since we have A is equal to BH, the area, and IX is equal to 1/12 BH cubed, then we get 1 is greater than 6EY over H, or EY is less than 1 over 6H. So what we're trying to say here is basically if negative H over 6 is less than or equal to EY is less than or equal to H over 6, then will either be stress 0 or in compression, so not in tension. And this is the answer we're looking for. So this question is more for just kind of understanding what's happening. This is sometimes referred to as the middle third rule. So what I just derived here, sometimes we call this the middle third rule. And what this is a rule that allows us to figure out where we can place loads to keep systems in compression. And can you guys think of a situation where we would definitely want to keep members in compression? Okay. Maybe you want to think of a member or a type of system or a material that performs really poorly in tension. So the kind of ding, ding, ding answer here would be for concrete or for stone, masonry systems. Okay. This is super important when we're loading columns or arches. So for columns, okay. And with specifically with rectangular cross sections, because we said that the area is BH, and what happens here is we have very little tensile support. So we don't want to force these loads or let these loads go into any kind of area that's going to cause significant amounts of tension. So we want to keep it in this specific block or this specific area that won't cause the system to go and experience tensile stress. So here is the second part. This is part B actually, which we don't have to worry about how to find this, but this is what they're asking for. Show us, you would just need to use that eccentricity, but show us where we can put P on this block, basically, so that we will only experience compression on this system. Okay, so that concludes everything for combined loading. Again, not much new theory in here, probably stuff that you've already kind of gone over. I know that some of these examples were a little bit heavy, but I'll post some suggested problems for this topic that will be more representative of what you're expected to know. A lot of these are a little more theoretical, so I wouldn't ask you questions to reproduce the math part of this. This was just to expose you to it and let you know that this stuff is out there, and we can use this type of information to solve these types of problems. But for this topic, I would refer more to the suggested problems. But if you have any questions, as usual, let me know. Leave it in the comments or just shoot me an email.